And of course, it's hollow. It's like the shell of a circular hyperboloid, which is what a circular hyperboloid is. It's not actually filled in, right? The question is, if I attached a ground to this edge and then another body up on this top surface, and I just fused those on, how would that be able to move? Would it move with the same freedom space as this guy? Well, hopefully you can visualize no. The question is why, though? It lied on the exact same surface. Well, the reason is because, well, first of all, is this even a parallel element? Well, sure it is. You could directly connect this body and that body on top with all blue lines that pass through the entire surface, and you could fill the whole thing blue. So it is a parallel element. The trick is, though, this is a doubly ruled surface, which means there's one set going this way and one set going this way, and I've drawn the set going that way as dotted blue lines, but I've never used that convention, so I kind of wish I hadn't done that. But it's nice for you to see and tell the difference between the dotted ones and the solid ones. They're just the two different the two different sets of lines in the double ruled surface. Okay, but they're all constraint lines, and which is why they're all blue. They all can pass through. They can all satisfy those conditions. They directly connect the two bodies. They don't ever exit the geometry. And they can fill the entire thing going either way, either this ruling or that ruling of lines, right? So it's definitely a parallel element, but what is its order of constraint? It's obviously not over-constrained, right? Because it's a self-contained single element, and no element is of itself over-constrained according to our definitions. What's its order of constraint? Well, there's 3 from this set, the circular hyperboloid, then there's 3 from the dotted set. So since there's 2 rulings and each ruling has 3 independent ones in it, then this one has an order of constraint of 6. Okay, so 3 from one set, 3 from the other set. It's 6 order of constraint, and therefore its freedom space is nothing. It doesn't move. It's a structure, and if you use this to join 2 rigid bodies together, it would be said to be totally exactly constrained. Okay. Okay. Even though technically you're like, well, wait, there's tons of redundant blue lines in there, but no, it's a self-contained single, element. Elements can never be over-constrained, or it's not useful to consider them such. They just have orders of constraint. This is an order of constraint of 6, and therefore it would be totally exactly constrained and would act like a structure. There would be no degrees of freedom. And this is, of course, why people make roofs and water towers and stuff out of this shape, because it's actually, as long as you have both sets of rulings, either in the shell form or as trusses, straight beams, it's actually a very stiff shape that constrains all directions. Okay. But if you cut this shell open, and you make sure that you cut it such that there's no blue line in the remaining geometry from the other set, the dotted set, then you're only accessing one set. Okay, and that's why this guy, the only blue lines that satisfy the 2 conditions of a parallel element are these ones from this set. Okay, they connect the 2 bodies, they pass entirely through its geometry, and they can fill the whole thing still, but there's not a single blue line that can satisfy that condition for this sector. If we tried to draw any of these other blue lines, you could draw them so they connect the 2 rigid bodies, but it would exit this geometry and violate one of the conditions. And if you make it so that none of them can fill it, satisfy the condition, then you're only accessing one set, one ruling. And in which case, this is an order of constraint of 3 and gets a freedom space with 3 degrees of freedom. That also looks like a circular hyperboloid. Okay? So that's a little trick there. Okay, so just make sure, you can calculate for the circular hyperboloid how big this arc needs to be before you can allow one of these lines in. But you can also be conservative and just make sure it's nowhere near. Okay? Okay, so how do you generate parallel element geometries? I want to equip you with the ability to not just have a library of these like wires, blades, living hinges, but be able to design totally original ones that no one's ever seen or heard of and have access to the infinite library of them. Well, how do you do that? It's fairly simple. It's very similar to designing parallel systems with wire flexures in many ways, but there's a few tricks here. Okay, so step one is you identify what degrees of freedom do you want that element to achieve, and for this example they wanted 3 intersecting rotations and a translation. Okay, step two is identify the corresponding freedom and constraint space. Well, we know how to do that. Freedom space of this guy is that guy with all its screws, and its constraint space is that. You can find that from the chart. Okay, so now that you know the element's constraint space, here's where the new stuff comes in. Okay, so the third step is use the constraint space, in this case it was a disk, to visualize the geometries of various parallel elements that, one, are entirely filled with blue constraint lines from within that space only, and two, directly join the element's rigid bodies. Okay, this is very similar to the two conditions that make a parallel element parallel, obviously. Okay, but it's also important the element must contain enough non-redundant constraint lines M from this space to satisfy 6 minus M equals N, where N is the number of desired degrees of freedom. So, for instance, say we wanted to get this number of degrees of freedom, or that set of degrees of freedom. Well, we know the element has to lie within this disk. Well, couldn't we have just picked a wire within this disk, say a single wire from there to there? That would lie within this constraint space, right? It would have a blue line that entirely fills, let's see here. Use this to visualize the geometry elements that are entirely filled with blue constraints from within the space only. So within this space, there is a blue line there that would entirely fill the wire, okay? And it would directly join the element's rigid bodies together, okay? So if we could, you might think, well, let's just, to satisfy these two conditions here, a wire would work. It would fit within this constraint space. It would be entirely filled, and it would connect the two rigid bodies. So we should be good. Wrong. You have to also make sure that it satisfies this. So since there's 4 degrees of freedom here, 6 minus 4 is M would be 2. So you have to satisfy these conditions, but make sure you pick at least 2 blue lines in there. Okay, and in this case, here's one example. It's basically a blade that's cut, pinched off at the center here, and widens out. It's like 2 V blades kind of stuck together. Okay, and you can see, sure enough, it can, if you recognize that the ground or one body is here and the ground other body is there, you can recognize that those bodies can be directly connected to each other without ever exiting this guy's geometry. Okay, and all those blue lines lie within the disk that we're trying to synthesize this from. And then it can also fill the entire geometry. We could draw every single blue line, make this entire thing blue. Okay? And there's, of course, 2 independent blue ones in there, and so it satisfies 6 minus M equals N. 6 minus 2 equals 4, right? Okay, so you can see how this works. So you get the constraint space, you know what freedom space you want it to achieve, you get its constraint space, and then you visualize geometries that have blue lines that lie within that constraint space and satisfy the 2 parallel conditions. Okay, that they directly connect the bodies, they don't ever exit the geometry you synthesize, and that they can fill it completely blue. And if you do that, it'll be parallel and it'll achieve the freedom space you want. And just make sure you also have enough independent blue lines in there to satisfy this. Okay? Okay, so that's one way to generate. So this guy, if I connected the ground to a stage, would achieve these 4 degrees of freedom centered at that point there, oriented like this, right? Okay, so you could visualize that. Be a rotation up there, a rotation here, a rotation up there, and a translation, okay? And this would constrain all the other degrees of freedom. And it's indeed a parallel element, okay? And it's order of constraint of 2. So it's not over-constrained, it just has an order of constraint of 2. It counts as 2. Okay? Okay. So let's look at other interesting ones and thereby learn some tricks here. So say you want to get, basically like a spherical ball joint kind of degree of freedom where you get 3 point in a sphere. How do you get that? Well, you could get the constraint space, and you could follow those rules to synthesize, elements. Imagine geometries of elements that can be that contain blue lines within the constraint space of the sphere that directly connect its two rigid bodies together, pass entirely through its geometry, and never exit at any point, right? And can be totally filled with blue lines. So it's a parallel element, and make sure you just pick enough blue lines in there that there's three independent ones. So the things that satisfy those conditions is this nub flexure, which is essentially like a wire flexure that's super short. Okay, and again, this is just approximate. To be really accurate, you'd want basically a shape like this: two opposing cones that just touch right at their tip, and then are short. That kind of approximates a nub flexure here. But this one's a little clearer. Of course, the diameter there would need to be infinitely thin to be super accurate. Okay, but this is approximate, right? And then this one, you might look at this one and you say, well, this is actually two elements. We took these two of these guys and laid them together and just joined them in the center. So does that count as a single element? Yes, it does. Anytime you take, anytime elements are fused together, either at a point or a line or a curve or whatever, if they're fused together as a single element, they count as a single element. Okay, and so this one, the two bodies that would join would be this and this would have to join the same body, ground. You can see it's thatched. And then this top and this top right there, they'd have to be joined to the same and the other body, okay, of the two bodies. And if it did that, it would be considered a single element because it's fused together in the center, and it would have an order of constraint of 3, and it would move like this. That top body with respect to the ground would move like a sphere centered around that point, a red sphere centered at that point. Okay. Same thing with this one right next to it. This is basically the same, two opposing V flexures, but they're fused down this central axis, and so they can't count as one element, and they move the same way. Okay. All right, and then if you take basically a funnel, a hollow shell of a funnel, and you either bring it down there or cut it off any place, and you get it infinitely thin, you could see there's no. And if you connect, the ground or the stage up top and down here at the bottom, connect something on there, you would see it would also move like this because the only lines that can connect the two rigid bodies that pass entirely through its geometry without exiting and lie within the sphere. And you can see it could make it entirely blue. You could see there's enough independent blue lines in there that it would achieve this. So this is another one that satisfies it. And it could be a full, funnel, or you can cut it in half like I've shown here, or cut it in any sector size here, and it would essentially achieve that same freedom space. Okay, that may not be terribly intuitive, but if you catted it up and you put giant blocks on both sides, and you did a modal analysis, you'd see the first three modes correspond with these three rotations. Okay. Okay, and sometimes these get a little messy, especially when you compare it with modal analysis. It may be that the fourth mode shape is associated with a natural frequency that's not so much larger than the three of its freedom space. So. Depending on how you design it. Of course, the thinner the walls, the more accurate. Okay, once these walls have any finite thickness, you can actually angle other blue ones in there, and it'll actually act like a structure. It'll lock it up. Okay, so Anyway, though these are all parallel elements, and they all achieve the same freedom space in theory, right? Okay, so here's two examples of other flexible elements, parallel flexible elements that achieved a single rotation. Okay, remember we showed you the living hinge, but this is a slightly different one. This is two triangles cut out of two opposing kind of triangles. Here they all lie. The rigid body's on top and this rigid body's on the bottom, and sure enough, this satisfies the conditions. blue lines can be drawn connecting them that never exit the geometry, and they can fill the entire thing blue. Okay, so it's a parallel element, and we get a nice rotation. This one is a famous flexure that actually does a really good job with the rotation. It's basically two blades fused together at 90-degree angles connecting the two rigid bodies there. And since they're fused together, they're not considered two blades. They're considered just one parallel element that looks like that. I think it's called a crucifix, or not a crucifix. Anyway, something like a crucifix flexure or something like that. Crucible flexures. Anyways, I'm forgetting the name of it, but this has a name in the literature where you get, it's basically a cross flexure extruded. Okay. Maybe it's cruciform or something. Anyway, you can look it up. Okay, and you can see, you could draw blue lines that directly connect those two things without exiting its geometry and entirely fill it. So it obviously satisfies the parallel element condition. Okay, and it's obviously within this constraint space and has enough independent blue lines that it satisfies this and therefore achieves the nice rotation. Okay. Okay, so other ones, and I'm going to stop talking about the condition here just in the interest of time, but if you want to achieve some really interesting freedom spaces, this is a 2D freedom space. Here is a flexible element that lies within this constraint space, as you see here. We've oriented it the same as there. So, here would be a ground, you can see thatching there, or a stage, and here would be ground or a stage on top, that, and that. It would attach on top there. And for those attachment points, you can see this satisfies the two conditions, and it would achieve a rotation through this dotted axis and a rotation down here. Okay. Okay. This one's an interesting one. Remember the two disks that are kind of offset previously. Okay, that we did in the previous lecture where we designed something that achieves this freedom space, but with 3 wire flexures. Well, this is a parallel flexure element where if you attach this and this face to a body and this face to a body, this entire thing will deform over its entire geometry. It'll be an element, and it'll certainly be parallel because its entire geometry satisfies those two conditions. Blue lines connect them, they don't exit the geometry, and they fill it entirely blue. And they're basically like two kind of those V blades, like two V's together, except they're kind of offset. This is like a V blade here, and that's like a V blade here, but they're offset. So you can see how it would achieve that freedom space. Okay, and then this one's very interesting. Okay, this one is a constraint space we're going to look at later. It's basically a bunch of nested circular hyperboloids, or you could think of it as a elliptical hyperboloid or hyperbolic paraboloid that's rotated around its center to achieve this as well. And you can kind of see that here. If you want to achieve your disk of screws with the same pitch, which is what that freedom space is, okay, then you could get a parallel element from within this geometry. And you can see this is basically a hyperbolic paraboloid flexure, this one that goes through there. And this is another hyperbolic paraboloid flexure that would have, and they're fused together down this central line. And you can see that any two opposing ones, this one on this side and this on that side, or this on this side and then on that side, two from each of the hyperbolic paraboloids, the same distance away from the center, lie on one of the circular hyperboloids in there, and as they go out, it's more and more nested circular hyperboloids. Okay, until finally the one through the center is right up the center there. Right, so you could have 3 of these hyperbolic paraboloids and space them axisymmetrically. It would work just as well. Right, but anyway, you can see if it's grounded down here on this side, and you stick something on top here, another rigid stage. It would be a parallel element. It would be one element fused together. The blue lines would directly connect things without exiting its geometry because they're ruled surfaces. And it would fill the whole thing blue. And it would achieve at the neck of this elliptical hyperboloid here, you can see right here at its neck would be the plane where it achieves its disks. Okay, if you attach that. Okay, and that one, by the way, we've stopped talking about order of constraint, but the order of constraint is always 6 minus its degree of freedom number, 6 minus 2, so that would be an order of constraint of 4. Okay, this one's really interesting. This one is basically consists of, that's a flat blade there, that's a flat blade there, that's a flat blade there, but they're connected by these curved like half cylinders. So it's kind of serpentines its way down here. And this is an example of something that it really, you can't just I can't just give you that shape and say, is this a parallel or a serial element? Because it depends on how you connect it. Okay, if you connect one of the rigid bodies on this side and the other rigid body on that side, then it definitely doesn't satisfy the condition of a parallel element. It would be a serial element. Okay, it would not work. Okay, but if you connect this back side that you can see with thatching here to a ground or a stage, and then you connect this front side, okay, to another stage, so you kind of sandwiches it like that, then that is a parallel element. And you can see its entire geometry can have blue lines that connect those two rigid bodies and pass entirely through its geometry, okay, without ever exiting at any point, certainly on the plane. You know, and then it could fill the whole thing blue. But you could say, well, that's true of the plane because there's basically 3 planes here. But then what about these guys? How would these guys work? Well, sure, because even if they're infinitely thin half cylinders, you could draw parallel blue lines that are, you know, you can see that parallel line, you can see that parallel line. Any parallel blue line could be made to connect the two bodies, pass entirely through its geometry without exiting, and fill the entire thing. Okay, and again, if that shell was infinitely thin, then it would obviously work better. But what ends up happening is this entire space lies within parallel stacked planes, you know, infinite number of parallel stacked planes, and its freedom space is a translation. So if you stuck, you know, a ground on this back side and a front stage block on this side, its first mode shape would be a translation. Okay, and then its other mode shapes would be who knows what, and they may actually be associated with natural frequencies that aren't even that much larger. So it's a little gray area here, but according to fact and ideal constraints, the freedom space of this would be a translation, and it would pretty well correspond with modal analysis as well, as long as you make the stages really large, right? And you know, the thing I don't like about modal analysis has nothing to, you know, it has a lot to do with the shape and size of the stages you join to, and almost nothing to do with the constraint. I mean, it obviously has to do with the constraint, but it has to do with both, and I don't like that definition of a degree of freedom. And I think this is, you know, fact's definition of degree of freedom is much cleaner. It's the black and white idealized scenario. Okay, so. Okay, so here's another interesting one. Say you want to get a tip-tilt element. You remember just 2 intersecting rotations that gets basically a disk of rotations. Its constraint space is you know, the sphere with a coplanar plane, blue plane. Okay, and you know, these are very interesting solutions. This is basically like a V blade flexure and then just a normal blade flexure kind of fused together. You can see as long as you ground this back edge that's thatched to the ground and then this front edge right here to another stage, you could satisfy all the parallel conditions of an element. You could draw blue lines that directly connect those without exiting the geometry, and you could fill the entire thing all blue. And sure enough, it would have enough blue independent lines in it that it would you know, achieve this guy's freedom space, and it would have a disk centered right there and in this plane. And that stage would move like that. And even more interestingly, look at this guy. So say this was basically like a flat blade here on this plane, but then this was some bizarre curved surface that's like a hollow shell that's infinitely thin, and it just makes sure all the blue lines that lie on that and satisfy that condition, you know, where this back thatched edge is like a ground of the stage and this front edge would be the stage you attach it onto. The blue lines would directly connect them, wouldn't exit the geometry, and would fill it entirely blue. So you get the disk centered right there, and it would be about there, and that's where the freedom space would be. Okay, this is another, and by the way, those two, of course, the order of constraint of those would be order of constraint of 4. Okay, this one is another one that I couldn't just give you the geometry and say is this parallel or serial, because if you joined this edge over here to a body and then this edge to a rigid body, it would not be a parallel element, it would be a serial element. Okay, it wouldn't satisfy the condition. You couldn't find any blue lines that satisfy those conditions. Okay, but if this back edge and that back edge and this back edge attached to a ground or a stage, and then this front thing I'm tracing there attached to a stage, so essentially like that, then it would be parallel. And you'd see this would be basically 2 blades, and this would be like a nice curved cylindrical surface where only parallel lines lie on its surface, as long as it's infinitely thin and fairly curvy here. Then it basically, you achieve this constraint space where you have the plane, and you have these angled blue lines on both sides here, and then these just purely lie in a box. Okay, and so there'd be an order of constraint of 4, and it would achieve this freedom space. Now, if you got rid of these 2 side planes and you just had this curved thing, then you would just have the box, and it would be this one, it would achieve this freedom space. Okay, but with these 2 blades on the side fused to it, you get this freedom space. Okay, and it's a parallel element as long as you're connecting it to the 2 bodies as I explained. Okay, this one is, it just keeps getting more and more interesting. These are constraint spaces you're not entirely familiar with, but this is a bunch of stacked parallel planes of parallel blue lines where the blue lines rotate at a very specific pitch, essentially. And another way to think of it, that the amount that they rotate as they translate is the same as hyperbolic paraboloids, as the blue line kind of rotates and translates through those. And so you could think of these as a bunch of hyperbolic paraboloids stacked next to each other, kind of like Pringle chips are stacked, right? Right, and so this is basically 2 hyperbolic paraboloid kind of flexures fused together that go up in an interesting way, so that they, if this back edge is thatched, stuck on a body, and this front edge here is stuck on a body, then the entire thing can be filled with blue constraint lines from this constraint space and satisfy all the conditions of a parallel element, and it will achieve this plane of blue screws, which by the way would be on this plane, and they'd be perpendicular to those blue lines, and they'd all have the same pitch. Okay, and that's considered one element. Now, this is another interesting one, and at this point, I promise this is the last one. I'm showing you all those infinite ones, right? But just interesting things. If you got these, here's a very interesting shape where I got blue lines, and as I advanced it forward and rotated it, I rotated it forward, and then I started rotating it back to get this interesting shape. So notice, the way you could connect it in the front and the side, but that would be that would not be a parallel element if you connected the ground and the stage here. But if you do connect the ground down here, or the stage, which you can see the thatching, and the other rigid body up here, either the ground or the stage, you sandwich it like this, then it would be parallel, because this is essentially a ruled surface that has blue lines that connect the 2 bodies, never exit the geometry, fill entirely the geometry.